Okay, so we just started talking about folds and how folds often happen in ductile deformation, right? Usually because of higher pressures, higher temperatures, usually deeper down in the ground. So very common in places where you have metamorphic rocks and stuff like that. Okay, so when you have ductile structures or folds, they're usually related to convergent boundaries, or when you push them together. For example, in this case, we have what we call first an anticline, which means that we have a convex fold, okay, where it's kind of like an A shape. If I did an A across this, it would be the top of the A and going down. We call that an anticline, okay. If I flip this over and it was going down like this, okay, we'd call that a syncline. Often I do this by the bottom of that S, right, okay, for S for syncline, and the structure of an A for anticline, right? Now, realize that anticlines and synclines go hand in hand. So as I get a material like this and start pushing on it, one side goes up, one side goes down. So you have an anticline with a syncline. So it goes up and down as it goes, right? Okay. Very common for anticlines to be related with syncline pairs. Now, a monocline is where a fold of one of the limbs dips in the same direction of the other one. So it goes like kind of something like this. So it doesn't bend all the way around, right? Okay, it only bends a little bit, and we call that a monocline. Okay, it's inclined, and this limb is going in the same direction as the other limb. Okay, not opposite directions, the same direction. So that's a monocline. Now, if I had something, let me get this ready, okay? Here's my surface again, my layer of rocks. Now if I had something in the middle here pushing up on it, okay, we'd call this a structural dome, where everything's dipping away from that center. Okay, so it's a structural dome. Now if that was upside down going the other direction, we call this a structural bowl, right? Okay, or a structural basin. And there's different ways that these can happen. A structural dome can have anything that's pushing up on it. So let's say a magma body that's pushing up on it, causing a dome. Or a salt can flow when it's under pressure, so it might actually push up over it. Okay? Or sometimes when you have large-scale features from compression, some places will go up in one location, down in another location to form these different types of structural domes or basins. Okay, so we'll show you some examples of these as we go through here. So here's some folds. Okay, here's your anticline here. Oh, my pen didn't work. Okay, there we go. Here's your anticline, your syncline, right? Now, lots of times when you have an anticline, your oldest rocks, which are the ones further down, are the ones that are going to be in the middle. Whereas a syncline, notice that the youngest rocks are actually in the middle. So that's a common reference that you see here. So if you look at this one right here, this is a syncline, right? Okay. The rocks on the top are the youngest, and those ones are the ones that are in the middle. That's what we call a syncline. Whereas on this one right here, okay, if I cut this away, the older rocks down here are going to be in the center. So this would be your anticline. This would be your syncline. Okay. Now this one right here would be a little bit more problematic. You can see that it's on its side here. Okay. And so we'd probably call it a plunging anticline, something on its side of that side, or an overturned limb. So you can see this one here where it's getting overturned and it looks kind of at a sideways glance. Okay. So this would be your anticline, anticline here, syncline here, and then an overturned guy here. I'm not going to go into the details of those, but I want just you to understand the basic ones of your anticline, your syncline, and a monocline. I don't have a monocline in this picture, but it's basically the same kind of thing. So here's another example. You can see all these pairs of synclines and anticlines together. So if I look at this rock unit, it goes up and down, anticline, syncline. This, by the way, is the Himalayas. Okay, and you can see the Himalayas, if you remember, is this compressed two convergent boundaries, two continental boundaries coming together, forming these big mountain ranges. And you have all of these anticlines and synclines all over the place, right? Okay, because of the compression that you have from that area. Another example of anticlines and synclines is here in the Appalachian Mountains. So when we had, remember, when we had all those plates slamming into the Appalachians, forming our mountain belts, we're pushing stuff on them. So we'll have, in our ductile deformation, we'll have thrust faults, which we do. We have thrust faults in the Appalachians, but we also have a bunch of folds. And some of these folds have now been exposed. So you can see them here. They look on its side and been cut into a little bit. We call this the Valley and Ridge Province of Tennessee or Pennsylvania and stuff like that. So here we have coastal plain, which we live on. The Piedmont is that kind of hilly area before the Blue Ridge, okay, which basically it's been eroded away portions of those mountains. Then you have the Blue Ridge itself, and then right behind it, just like in a carpet, as I push that carpet along, it's going to be crumpled up along behind the back, right? So if I push this and I start pushing on it, it's going to get crumpled, and you start getting these nice little anticlines and synclines. So that's really what's happening behind us here in the Appalachian Mountains, is you have these synclines and anticlines going all the way throughout the area, forming these ridges and valleys as they slowly erode away. Okay. So, however, those same features, as you push in large-scale regions, you can get places that have big domes in some places and big basins in others. A good example of a dome is here in, this is Mount Rushmore, and here you have this igneous body pushing up at the bottom, pushing up all the rocks around it, okay, to form this dome-like structure in the middle. Okay, so here's that granite, that igneous body coming up, okay, and then forming this dome around the region. Okay, so here's Harney Peak, where Crazy Horse is, and here's Mount Rushmore over here. Okay, now this one is the same kind of feature, but now it's been depressed a little bit, and so now you have this the Michigan Basin. It's all been kind of sheared away, but we have this kind of basin formation around here. You can kind of see it here, but it's not a bowl per se, because a lot of it's been sheared off the top. Okay, but that's an example of a basin. So here's some examples of some pictures that I'm hoping that that you'll be able to recognize. Okay, come on, there we go. Okay, so this one right here is this. What kind of system is this? And this is what we're going to do in your discussion page this week. You're going to try to identify structures and relate them back to some kind of tectonics, the kind of plate boundary, also what kind of stress is applied to it. Is it a normal fault, a strike slip fault, right lateral, left lateral, all that kind of stuff. You're going to be identifying them based off of some pictures. So some of them are always easier than others, and I just want you guys to look at the clues to be able to understand what we'll see in the future. Okay, so for example, this one. You can see multiple faults here. I'm going to actually look at these fault planes. So here's this one, because we're using this guy right here, this here as our marker bed. It's just not working very good. Okay, and here's another one there. Okay, another one here. Okay, there's some other ones throughout here. Okay. Another one there, another one here, okay? But all different kinds of faults. This is your footwall. Okay, it's freezing on me here. My hanging wall, okay? And so this block's gone down, this block, the footwall, has gone down relative to the hanging wall, so we call this a normal fault. The extensional regime, okay? So it would be related to kind of divergence in the system. This is actually a dome. You can see the beds actually dipping all away from the central location and going up. I know it's hard to see from this aerial photograph. And you can see the actual circular feature right here, and they're all kind of going up. So this would be a dome. Okay. This one right here is a little tougher. You can see the rocks going up on this side, okay, but they're also going up on this side. And so the middle has been eroded away. So this would be an anticline, okay? So that would be a compressional feature. Okay, come on. There we go. This one, these two are both strike slip faults. You can see the fault plane right here, and this one has two of them, one there and one there. Notice if I was on this block right here, this is moved to the right. So this is a right lateral strike slip fault. Okay. Also, this one here, you see this one, the stream goes down and goes off here to the right and then down again. So if I was here, this block looks like it's going to the right. This is also a right lateral fault. This is a fault scarp. This is the hanging wall here. Sorry, the foot wall here. I did that wrong. Yeah, I should stop trying to do this. And down here is the hanging wall. And this is the scarp left behind. Okay, and so this is a normal fault. You can see this one. This one's pretty easy. This is a syncline as you go through the features here. Once again, a compressional regime. Okay, here is one here. It's kind of a broad anticline. Okay, compressional regime. This is also an anticline. It's the one that's been eroded away. I'm not going to give you hard ones like this. I'm going to give you more easier ones in our readings, like this one here, or maybe the faults that I have, the strikes that faults I have in here, or maybe some of these ones in here. This one here is a good one. This one here is a good examples. Here you can see two faults here, one right there, one right there. The hanging wall is going down relative to the foot wall. This is a normal fault, therefore divergence. Okay, so that's something you're going to be identifying in your discussion this week. Okay, so which of the following here is an example of plastic deformation? Let's just review real quick. Now remember, a joint is something that just breaks apart. Okay, no movement along it, so that's your joint. A fault here is one that actually has movement along it. So the right answer is up here. It's the fold. It's the one that actually where you have bending here, right? That's ductile deformation or plastic deformation, just like my silly putty. Which of the following processes can cause uplift and produce mountains? Well, this is kind of related to some of the things we just talked about, and we'll talk about it more in just a second. Anytime where we have crustal shortening and thickening, we're probably going to have mountain building, right? Okay, so that's a divergence and convergence like that is going to cause mountain lifting. Okay, if I remove lithosphere on the mantle, it's going to cause things to go back up from isostatic rebound, and so that will also happen. Okay, but thinning and heating of the lithosphere could also cause mountains, because remember, if I pull these apart, you can have one go up and one go down. So in reality, this is kind of a trick question. This is all the above. All of these can cause mountains. Some of them are bigger than others, but they're caused by different forces as you go through it. Okay, so major mountain ranges, these usually occur in places where we have some kind of a plate boundary interaction. Okay, all mountains in the world are a result of some kind of plate boundary interaction. Some of those plate boundaries are no longer occurring, or there's some hotspot relative material with it or something of that nature. But all of them have in past been there. Like the Appalachians is a good example. It's not that Appalachians are not actively building today. They're actually decaying, because at one point Africa, Eurasia slammed into North America, forming the big mountains. But now as you slowly go away, they slowly are eroding away. Whereas here on the western United States, these mountains are actively being built. Okay, now the mountain building process is what we call an orogeny. Okay, is an orogeny, the process of mountain belts formation, usually caused by convergence. Okay, but you can have it in other places too, but usually by convergence. So you can also, like I said, you can also get mountains from rifting, from pulling things apart. Okay, like this with the horst and the grobens here, where the horsts are going up, the grobens going down. Okay, so that's caused by rifting. And your example is the Basin Range in the United States. I'll show you some examples of that. Also happening in the middle, the African Rift Valley of Africa, where you have finding these rift valleys in the middle where you have the lakes and things like that. So some volcanics come up through it because it's thinner. Okay, as it goes away. Okay, or you can have things where two plates are coming together. Okay, like in this example where we have an ocean plate coming in with continental plate. Okay, a good example might be this. Would be the Cascades in northwestern United States, and forming the volcanic island arc of like Mount St. Helens, Mount Hood, and all those different volcanoes. That's a great example. The Andes might be a good example of this one too. Okay, we'll stop here and we'll start up on the next one for the rest.